Good morning, friend. Today we are going to discuss about spring pendulum, the topic in simple harmonic motion. Before discussing about spring pendulum, we'll go for spring system. What is there in spring system? Okay. So here is in a diagram, a common diagram which shows spring system. Okay. Here, a spring having a spring constant K is suspended from a rigid support. Okay. And free end of a spring is attached to a load of mass M. As you know that whenever spring is compressed or stretched from its natural length, then restoring force is produced. Okay? And this restoring force obeys Hooke's law. Now, most important thing is that what is natural length? Whenever the spring is not compressed or stretched, what is the length of the spring? That length is called as natural length. Whenever a force is applied, okay, the natural length will get changed to another length. The change produced in the spring, that is nothing but displacement, and that displacement will be away from main position. But according to Hooke's law, the restoring force tries to bring the coil towards its main position. Okay? Hence the equation becomes Fr equal to minus Kx, where Fr is restoring force and X is the displacement from main position. As you increase the displacement, restoring force inside the spring also increases. The K is nothing but a proportionality constant, which is also called as spring constant. One more thing, negative sign in the equation indicate that the restoring force and displacement are always in opposite direction. If you stretch the spring in downward direction, then restoring force will go in, try to pull it upward direction. When we compress the spring in upward direction, then the restoring force try to push in downward direction. So the work of restoring force is nothing but to bring the spring system towards its mean position. Okay? The most important part in this point is K, that is spring constant. Okay? So from this equation you can get the unit of spring constant. What is the SI unit of spring constant? That is Newton per meter. CGS unit of K is dyne per centimeter, and dimension R L0 M1 T minus 2. Spring constant. These are the units and equation of spring constant. But what is the basic concept of spring constant? Spring constant is a measure of stiffness of the material. Higher is the spring constant, higher is the stiffness of the material. Spring constant depend upon radius of wire which is used in the spring, length of the wire, and the material of the wire. Okay? Our equation given for spring constant is K equal to G dq upon 8 eta d raised to 4, where G is the shear modulus of the material, D is the diameter of wire which is used in the spring, N is the number of turns, and D is the mean diameter of the turn made by the wire. Whatever the coil's turns are made by the wire, that mean diameter of the wire is D. Here you can see the spring constant depend upon shear modulus, means elasticity of the material. So as material changes, spring constant will also change. Spring constant also depend upon D, that is diameter of wire. As diameter of wire increases, the spring constant may increase. Another factor where spring constant depends is the length of the spring. Okay, so if the length of the spring changes, then spring constant also changes. The relation between spring constant and the length of the spring is given as K is inversely proportional to L. So wherever length of the spring is more, there will be less spring constant, and wherever length of the spring is less, there will be more spring constant. Okay? So according to this equation, we can explain one more point, that whenever a spring is divided into two equal parts or two different parts, what will be the effect of the spring constant on the spring constant? Suppose a spring given here, a spring which is there here having length L is cut into two parts. Now you can see that L is the length of the spring which will be cut into two parts. Okay. Now first part has length L1, length of first part, and L2 is length of second part. But one relation is given that L1 is N times L2. L1 is L times L2. Now what will be effect of spring constant on first part as well as second part due to the change in the length? Okay, that we are going to determine. Now basically you know that length of the spring is nothing but L1 plus L2. Sum of length of both the part will give rise to the length of original spring. Okay, so L equal to L1 plus L2. And you know L1 is equal to N times L2. So we can put there N times L2 plus L2. Here L2 will be common. So equation will be N plus 1 L2. So what will be L2? L2 is nothing but L upon N plus 1. So this is the relation between length of second part to the length of original spring. What is the relation? This is the relation. Similarly, you can write length of first part equal to N times L2. Now already we got the equation of L2, that is equation first. We can use this equation to get length L1 of first part. So N times, put the L2, L2 is nothing but L upon N plus 1. Now we got the relation between length of first part of spring, length of second part of spring with respect to length of original spring. Now we will determine the effect of this change in length on the spring constant. Okay, as you know, as we have discussed, that K is inversely proportional to length. As the length of spring will be more in one of the spring, then it has less spring constant, and if length is less, then it has more spring constant. So whenever the two quantity are inversely proportional, then the product always remain constant. So here KL remain constant. KL remain constant. Same equation will use to determine the spring constant of first part of the spring. Okay. So as we discussed, KL remain constant. So one equation we can form, KL equal to K1 L1. What is K? K is the spring constant of original spring. L is the length of original spring. K1 is the spring constant of first part of spring after it is cut. L1 is the length of the first part of spring after it was cut. Okay. Now we have to find K1, relation of K1 and K. Okay. Now here we can use the equation number second of L1. Directly put the equation value of L1 from equation second. So KL equal to K1 as it is. L1 will be N times L upon N plus 1. The similar factor is L. Okay. Then when you rearrange, what you get? K N plus 1 upon N equal to K1. So this is the K1, that is spring constant of the length of first part when the spring is cut into two parts. Okay. Similarly, you can find K2 with the same equation, that is KL will be equal to K2 L2. Put the value of L2 from equation first. KL as it is, K2 as it is. Instead of L2, what you can write? L N plus 1. Now rearrange it. You know L is a common factor, K on both the sides, and here K N plus 1 equal to K2. So this is the easy way to find the spring constant of different parts of the spring when it is cut. Okay, you can take ratio of this. When you compare K1 upon K2, what answer you will get? K1 upon K2 is nothing but, see what are the similar factor? K, K, N plus 1 are similar factor. So what will get? K1 upon K2 is nothing but 1 upon